this is Mrs. Brown, and today we're talking about scatter plots and the lines of best fit. So to start with, let's do a couple of vocabulary. Bivariate data is a fancy way of saying we have two variables. So like the amount of money you earn based on the number of hours. So hours and money earned. Those would be examples of bivariate data. You've got like those two variables going on and there's some sort of relationship. And so a scatter plot is how we graph that relationship. And we do it using ordered pairs. So if you're making, say, $8 an hour, that would be for 1 hour, you would get $8. So we would graph 1, 8. Now, obviously, if it was just straight that would be a straight line and we wouldn't need a scatter plot. But if it was a constant rate. But these are things that don't necessarily have exactly a constant rate. Okay. Because in the real world, a lot of times you don't have like perfect lines. And so that's where stuff like this comes into play. All right. So if we have what we call a positive correlation. So we got some dots kind of scattered here. And if they sort of kind of look like they're making a line that has a positive slope, it's a positive correlation. If you have some dots kind of scattered and they look like they're making a line that has a negative slope, that means you have a negative correlation. So again, you know that you read graphs from left to right, just like you read a book. And so if it's going up from left to right, it's positive. If it's going down from left to right, it's negative. So if it looks like it's kind of traveling up, it's a positive correlation. From left to right, if it looks like it's going down, it's a negative correlation. And then sometimes you have things that are all over the place and there's no correlation because it doesn't have a trend of going up or going down. So it's just kind of all over the place. There's no correlation there. Okay. So part of today is part of the skill is just being able to identify if there is some sort of correlation. Is it positive? Is it negative? Or is there just not really any pattern at all to the data? Okay, so let's take a look at a couple of examples. So let's say I had this graph with the money earned and hours worked. Maybe I asked various people or collected some data on things over a series of weeks. So looking at this, what kind of correlation is it? Well, it's kind of trending up. So if I were to draw sort of a line there, this would be a positive correlation because it's trending up in a positive direction on a positive slope. What does this mean? Well, as you increase the hours that are worked, you increase the money that's earned, which is a good thing. All right. When you look at this one, okay, again, I'm looking to see what kind of correlation I have. Well, it looks like everything's kind of trending down, kind of like I have a negative correlation. So this one would be a negative correlation because from left to right, it's trending down. And if you think about it, the amount of Halloween candy that you have left is going to be diminishing as the days after or days since Halloween. So if I was talking about the relationship, as the farther away from Halloween you get, the less candy you have in your bag. Okay? So again, that's an example of positive and negative correlations. In order to find a line of fit, today we are just going to be eyeballing it, looking at it and seeing guessing where about the line should be. So when we do that, we're going to make a scatter plot. We're going to draw a line that seems to be close to most of the points. That's kind of what I did here. I wasn't perfect. I wasn't actually trying to write an equation for that one. So I didn't even use a ruler. But again, it kind of gives the idea most of the data is kind of like in the center of most of the data, not perfect, but that's kind of what we're doing. And then we're going to write an equation of the line. We can use point slope form, or you can use y-intercept form, like y equals mx plus b, whichever one you're more comfortable with. And then use the line to make predictions. So for instance, if I have no data point like right here, and I wanted to read, I could use my line to guess what that one would be to make that prediction. Okay. So let's take a look. Previously, you learned about linear extrapolation, which means that we're going beyond the range of data to make predictions. So if I'm looking at my graph, it only kind of goes up to like 4 or something. So if I'm doing a linear extrapolation, I might be trying to figure out what it would be at 6. So I'm going beyond where the data is. A linear interpolation is predicting the values inside the range. So for instance, I don't have a value for what it would be when x is 2. But if I draw a best fit line, I can make a guess at what the prediction about what it would be at 2. And so that's kind of where we're doing the linear interpolation. It's a big word to say. Okay, so let me actually use a different color. And so we're going to practice this. I'm going to take my ruler, and it is much more helpful if you have a see-through ruler when you're doing this, because you can kind of see the data points. I'm kind of going to pick a spot I think is in the middle. It's not going to be perfect, and my ruler moved while I was trying to hold it and draw. Okay, so that might be my line of best fit. So if I were then going to write an equation to represent that, I would want to start by finding the slope. So it kind of looks like my point goes through here and here. It's not 100%, but this would be a change of 1, and this would be a change of 5. Okay. Again, these are going up by 5s, and these are 1. So rise over run means that I would have 5 over 1 or 5 for my slope. So when I'm looking at my form, if I'm just going to use slope-intercept form, because I can actually read the intercept pretty well right there, that's mx plus b. M is the slope, so I have a slope of 5, and I actually have a y-intercept where it hits the y-axis, looks at 5. So that would be the equation of my approximate best fit line. Now, if I wanted to know what it should be at, say, 4, because I do not have a point. I don't know what that value would be when x is 4. How do I figure that out? I just substitute it in. So I would do 5 times 4 plus 5 and get 20 plus 5 or 25. Now, again, my drawing's not perfect, so it doesn't actually go through that point, but theoretically, if I was drawing on a grid and everything was all perfect, it would go through that point. But you can see that it's about right there. And if I were actually had these equal size squares and not something I just kind of eyeballed, then that would in fact hit that. Okay, so that's kind of what we do when we want to make a prediction. And that would be interpolation, because of course we're like inside the range of the data. If I wanted to do 6, that would be the extrapolation. Okay, so again, finding the slope, using that to write my equation. In this case, because it was real easy to read the y-intercept, I went ahead and used slope-intercept form. But again, if you're having trouble with that on yours, you can always use point-slope form too. And then to predict a value, you kind of substitute that x value in and see what comes out. Okay, I hope this helps, and have a fabulous day.